try that again. There we go. Okay. So now we have CH3COO minus, and we have 2 millimoles there. What do you notice about those two? They are equal, and that's because we had exactly half. 2 millimoles is exactly half of 4 millimoles. So the base is half the amount of acid, so it neutralizes half the acid. Half of the acid is unreacted, half of the acid has turned into its conjugate base, okay? And this is going to be lovely because, guess what? We're going to have a Ka expression, right? Because, well, first of all, I guess we can calculate our concentrations because if we're going to use a Rice table, we need concentrations. So we take our millimoles of acetate, and that is 2 millimoles, and divide by the total milliliters. Our total milliliters, we had 2 milliliters and 4 milliliters, so our total volume is 6. So 2 divided by 6 is 0.333. The math is the same for the conjugate base because we produced half of it got changed into its conjugate base, so that is the same. So we now have both the weak acid and the weak base. So we can use either the weak acid equilibrium or the weak base equilibrium. So you can either put CH3COOH on the right and have it react to form the base, or you can put CH3COO minus on the right and have it react to form the acid. The math will work the same regardless. Which do you think will be easier? Which one will revolve less math? Weak acid, Ka, because you don't have to do anything like, taking your Ka and converting it to Kb. If you find OH, you would have to convert it to H and then convert it to POH, whereas this gets us right into hydrogen. So here is our weak acid equilibrium. So less math involved in that. CH3COOH in equilibrium with H plus and COO minus. Molarities of those are the same, but hydrogen starts at how much? 0, because if I don't actually mention it at the beginning, we just assume that it is 0 to start with, and we'll end up with some at the end. And then, of course, this is all 1 to 1 to 1. So we have minus x plus x plus x. We end up with 0.33 minus x, x, and 0.33 plus x. We write our Ka expression, H plus times CH3COO minus over CH3COOH. Plug in your Ka from your data booklet, which is 1.8 times 10 to the minus 5. Plug in your equilibrium things, and then you look at all those x's in that equation, and what do you say to yourself? Let's assume those x's are insignificant, because otherwise we would end up with an x squared term and an x term and an x term and a number term, and that would give us a quadratic, and God knows we don't want to do that if we don't have to. So let's not do that. Let's just assume x is insignificant. Okay? And that gives us, oh my gosh, now the math becomes glorious. Look at it. Do you like that? Because guess what? We have exactly the same amount of the acid form and the base form, right? These are the same. And so we just go, oh, I can just cancel those out. So X, which is equal to the hydrogen ion concentration, is equal to 1.8 times 10 to the minus 5. What is 1.8 times 10 to the minus 5? It's the hydrogen ion concentration, but it is also the Ka. So what we have discovered is that when we've neutralized exactly half of that acid, Ka is equal to the concentration of H plus when we've neutralized exactly half the acid. Isn't that lovely? Mm-hmm. So when we're titrating, and say our equivalence point is here when we've used up all the acid, when we get halfway to the equivalence point, if we stick a pH meter in there and we find the pH, we can actually find the Ka of the acid, because the hydrogen ion concentration halfway to the equivalence point, halfway to the equal point, is equal to the hydrogen ion concentration. If this is not making perfect sense right now, don't worry, we will also be looking at this in the context of titration curves. So hopefully by hearing it a few times, it will all click in and start to feel good, okay? But in the meantime, what we have discovered is that Ka is 1.8 times 10 to the minus 5, and H is 1.10 to the minus 5. So this is what we call the half equivalence point. That's where half the acid has been neutralized. And we can say that the concentration of H plus 1/2, and that little 1/2 refers to concentration of H plus when half the acid has been neutralized. H plus 1/2 is equal to the Ka of the acid, okay? Or if you prefer to do pH 1/2 is equal to pKa of the acid. Either of those work, okay? Okay. Now, I know I keep telling you that you could, because there's weak acid and weak base, you could use the weak acid equilibrium, or you could use the weak base equilibrium. Let us prove to ourselves that we would get the same answer using the weak base equilibrium. So, for example 1, our concentration of the acid is 0.6 molar CH3COOH. Our concentration of the base is 0.2 molar CH3COOH, that is COO minus. That we've already calculated that in example 1. Okay? Is that too big of a jump backwards, or can we live with that? Jumping backwards to example 1, we put some acetic acid in and we added some OH to it. So some of the acetic acid got converted into acetate ion. So now we have some acetic acid and some conjugate base. And we used a RICFA table and all of that and divided by our moles to finally get these molarities. Are we okay with just starting from here and seeing where we go with because we have both the weak acid and the weak base, We can use either the weak acid equilibrium or we can use the weak base equilibrium. And this time we're going to just try it using the weak base equilibrium. Do you guys think you could try this yourselves? Oh, that makes sense. Yeah. There you go. Oh, and Alan, this is your other quiz from long ago. There you go. Yoav, I have your quiz here, by the way. Yeah. So yeah, it made sense. No, it's yours. Do you know what? It's sometimes it's not go the same path, but good thing is solving does in your head, right? So you're solving it using what you know, which is better than like solving it by remembering something I taught you once. That's true. Right? Yeah. Oh, what have I done? Here we go. I'm like, hang on, I can't have the same species on both sides. Yes. Yes. I think I screwed up by leaving it there by accident. It wasn't supposed to be there. But I had already printed the print off, so I was like, okay, well, there it is. Oh, and that, look, I made the same mistake here. Oh, you know what? Let's go with this one up here because it's going to be better. Yeah, if you can just go like this, because it's not right. Okay, so ignore that. Yeah. I agree. I don't know. And you see how we're reviewing how do you find your KB, right? But you guys all did well on that on the quiz, so I'm not worried about you. Now, question, was I supposed to get 4.27? Did you guys get 4.27? You got 4.2 what? Good. Now, one thing I wanted to draw your attention to is I've been skipping a few steps here that I've made you write in the past. I believe that you will be okay on AP if you don't have to write POH is equal to, you notice I left out negative log of OH minus and I just tossed in the concentration. I think you'll be okay if you do that. There's no guarantee, but if you're pushed for time, if you're like, I'm in a time crunch, I just want to save a little bit of time, then do that. Yes? You need to show as much work as is necessary. So what you're going to do is you're going to write a lot of practice problems and keep referring to the answer key and the chief reader's report, because that's the only way to really know for sure, and we never know for sure. Sometimes they care about sig figs, sometimes they don't. You never know when they're going to be, sig figs count here, right? Sometimes you can just get away with anything, and sometimes they're like, nope, they matter here. So it's a bit of a guessing game. So we practice a lot and we do our best to guess. If you have time, I tend to err on the side of writing a little bit more, but if you are a slow writer, I would tend to err on the side of writing a little bit less. Yes? Okay. And you'll notice here I did not write PKW minus POH. I just left that out and went straight to 14 minus my POH, and that gave me my pH. I think that would also be fine. Okay. Now, Did you feel like you wanted to do the same exercise on the equimolar one, or are we good? Do you know what I mean by equimolar? Equimolar is equal amounts of moles. Daniel, I have your quiz. There you go.
No, like my phone died, so no longer.
Do we feel it is worthwhile to do this with the race table and the KB? No. Okay, then we are going to go to the conclusion of this. We're not going to do this, but we're just going to recall when the concentration of HA is equal to the concentration of A minus. What do we call that point? When adding OH minus to HA, when adding OH minus to HA, so that's what we're starting with. We're starting with just OH and HA, and we're reacting it until that is true. Chat with your neighbor about this. Elliot, I know you want to answer, but I need people to think. If you add OH minus to HA and you allow it to react until HA is equal to A minus,
Another day.
how did we get to, do you remember? We got to this point where we had the same concentration of CH3COOH and the same concentration of its conjugate acid. And we got that by adding NaOH plus, we added the sodium hydroxide into the CH3COOH, and we got NaCH3COO, and we got H2O. So we started with these, and at the end, we have this one and this one are equal. So the circledy ones are equal. The green ones are equal. So this is HA and A minus. Whoa. How many people feel like they're having some sort of insight? 1, 2, I know Elliot has. Go and talk to people and see if they can explain it to you. I know there are people who haven't put their hand up who probably have an inkling. Go find one of them and make them explain it to you.
Well, what's in your mind? I didn't just read the I know that
Yeah, no one.
Damn.
Okay, lovelies. What point are we at? We are at the half equivalence point. And this point is the point where we have done what? Neutralized half the acid. Because if we've neutralized half the acid, we have turned half the acid into its conjugate base. So if we were to do a KB for this thing, whoa, where do we go? Here we are. So if we were to do a KB for this thing, what species would we be using for our reactant if we were doing a KB? What would we be using? CH3COOH? That's an acid. Who do I put for my reactant when I'm doing a KB? If I'm doing a KB, my reactant must be a base. So if I have KB, the reactant must be a base.
That's what it is. You're like, oh man, I called it water. That's what it is.
At the half equivalence point, what is true? The CH3COOH is equal to the CH3COO minus. And therefore, we have it here. These two are equal. So we can say, oh, this is equal to this. And therefore, what can we do with them? We can cancel them because they are equal. So at the half equivalence point, what is KB equal to? So you could also use that equation. And recall from before, what does Ka equal? H plus. And that's at the what point? At the half equivalence point. Describe to your neighbor, what do we mean by the half equivalence point?
Let's go.
Yes, Alvin. The transition point of an indicator is the half equivalence point of that indicator. I noticed a lot of you were trying to use the word transition point here. Transition point is specific to indicators, but the half equivalence point is the same as, for an indicator, is the same as its transition point. Okay?
All of the transition points that have to do with
When we're talking about indicators, yeah, because transition point is specifically when something transitions from one color to another. So we can't make that a more general thing and say the transition point of this acid, because it doesn't transition from one color to another.
Can I refer when talking about
I would call it a transition point for an indicator, and for other acids, I would call it the half equivalence point. Yeah? Okay.
That's so satisfying the way
Okay, my friends, here we go. When all of the weak acid is neutralized and there's no excess NaOH, which means we have no excess acid, we have no excess NaOH. What do we know? If we've neutralized all the acid, what do we know about the quantities? When we've neutralized the acid, what do we know about the quantities of HA and NaOH that have been added? They have to be equal, okay? So let's see, what are my quantities? Well, I have 5 milliliters of my 1 molar base, and I have 5 milliliters of my 1 molar acid. So are those moles going to be the same? Five milliliters of 1 molar, 5 milliliters of 1 molar. Will the moles of each of those be the same?
Yes.
Yes. How many millimoles will we have of each? 5, because 5 milliliters times 1 mole per liter is 5. The liters cancel and we're left with millimoles. So we have 5 millimoles of the OH, and we have 5 millimoles of the CH3COOH. So now we're going to put that in our RICFA table. RICFA first. 5 millimoles and 5 millimoles. And we have, what did I do here? Oh yeah, that's right. So now we have nothing here because we've just started the reaction. Do you remember the last time I did this? I said all of at least of one of the reactants will get used up. Yes? Yeah. However, in this case, both of the reactants get completely used up because we are at the what point? When you have equal moles of each and they both get used up, what do we call that point? That point is the equivalence point. So when we have neutralized all the acid and we don't have any excess base, we are at the equivalence point. When these two are equal, we are at the equivalence point. Okay, so how much of the OH gets used up? All of it, 5 millimoles, sorry. How much of the CH3COO gets used up? All of it, 5 millimoles, which means we are producing 5 millimoles of the base. Take a look at your final moles. What do we have left? What is the only thing we have left? The conjugate base. So all that we have left at the end is CH3COO minus. We don't have any of the hydroxide. We don't have any of the conjugate acid. So we're going to find our concentration of the one thing we have, CH3COOH. 5 millimoles is how much we have left. What is our total volume? Go back to the question. What is the total volume? We have 5 milliliters and we have 5 milliliters. So our total volume is 10 milliliters. And so we do the division, and now we know the concentration of CH3COO minus. So we have only the base left. What kind of equation should we be using if we're working with a base only? We should be using Kb and the weak base equilibrium. So here is our weak base equilibrium. All right, so here's our weak base. And we're starting with 0.5 moles of the acetate ion. We have none of the other things yet, okay? And then, of course, we're shifting to the right. So we go up by X on the right and we go down by X on the left. 0.5 minus X, X, and X. What kind of a K value should we be writing for this? It's a Kb because we just did a weak base equilibrium. Weak base Therefore, KB. Okay, we write our KB expression. We go find the value of KB, which is KW over KA of the conjugate acid, and we get 5.56 times 10 to the negative 10. Plug everything in. We're plugging in our KB, and we're plugging in our equilibrium row, and we're going to assume X is much, much less than 0.5. In other words, i.e., assume X is insignificant. You can write it either way. And now we just do our math. Solve for X squared. X squared is equal to that number. Take the square root of both sides. And you get X is equal to 1.67 times 10 to the minus 5. We go back to our table and say, what was X? X was hydroxide. So that is our concentration of hydroxide. We can find the POH, and then we can find the pH. Yes? Okay. Who is the only thing that's going to be present at the equivalence point? When at the equivalence point, when adding a strong base to a weak acid, the only thing present is the conjugate base. I didn't really write enough room. There we go. Yes. I think it's 2 sig figs because we used a Ka that was only 2 sig figs. So it's only 2. Yeah. So a lot of times pH is sort of limited by either Kw or the Ka that you've gotten it from. So often it's just 2 sig figs. Yeah. All right. Can you imagine what we're doing next? We've done before the equivalence point. We've done halfway to the equivalence point. We've done at the equivalence point. Where are we going next? After the equivalence point. So how much of the weak acid is left after the equivalence point? How much weak acid is left after the equivalence point? None. Okay. So let's take a look at what happens. Now we have added excess strong base. So we are after the equivalence point. So in other words, we have more moles of NaOH. So here we have 6 milliliters of 1 molar NaOH. So how many millimoles is that? 6 milliliters of 1 molar NaOH equals how many millimoles? Honest to God, you guys should be telling me this answer with no problem now. 6.00, but I'm getting really lazy here because we're more concerned about concepts than sig figs right now, okay? So that's why I'm just writing things like 6 rather than anything more fancy. Now, our weak acid that we started with was 4 milliliters of 1 molar acetic acid. How many millimoles of the acetic acid did we start with? 4. Once we've determined the moles of the strong base and the moles of the weak acid, what tool should we use next? The RICFA table, okay? We're going to keep using that term, and I think we're all just going to remember it because it is silly, okay? The RICFA table. So here we have our hydroxide, and this, of course, is from the sodium hydroxide. But do you see how it's nice not to have sodium kicking around in this equation? It's just like, I mean, we could have sodium over here, but then it's like, ooh, if we put don't draw this, don't draw this, don't draw this. If we put sodium over here and got rid of that charge, then it kind of hides the fact that you have the conjugate base. Yes, it's more obvious that you have the conjugate base if we don't have that sodium kicking around. Is good? Okay. So start with 6 moles of OH. We start with 4 moles of COOH. Who's our limiting reactant? Yes, CH3COOH is the limiting reactant, and therefore we use all of it up, -4. It's all 1 to 1 to 1, so we got -4 plus 4. Forgot that plus. 6. Okay, so 6 minus 4 is 2. 4 minus 4 is 0. And 0 plus 4 is 4. So now we look and we say, who do we actually have something? I have something here, and that is OH. I have something here, and that is CH3COO minus. So what do we have left over? Our concentration of OH is equal to the 2 millimoles over the total volume, 10 milliliters, 0.2 molar. And we have CH3COO minus, which is a what base? It is a weak base. And what do we know about weak bases? Weak bases are mostly what? Undissociated. I'm going to say unionized because they need to pull off and become an ion. Like they don't actually dissociate. I know unionized and unionized are the same word. I love that. You have to go by context to know whether it's unionized or unionized. So if the weak base is mostly unionized, how much OH minus is it making? Your options are a lot, some, or a little. If most of it, I don't know why I put unionized. I don't even know what you call it because it's an ion on the right and then we produce some ion on the left. Most of it is unreacted, okay? Most of it just stays as it is, okay? Most stays here because it's weak. How much goes here? only a tiny amount because it is a weak base. So the weak base makes very little OH minus. You have two sources of OH minus. Two sources of OH minus. You have OH here from NaOH. And then we have very little OH and that is from the CH3COO minus. Okay, so the species present are going to be the weak base, and there's going to be a little bit of extra hydroxide. But if it's very little, what do you think that's going to compare to 0.2 molar? It's going to be insignificant. Yes?
I thought that most of it had to be on iron, so that it was very significant.
Okay, so the ionization reaction is this reaction here. This is the ionization reaction.
Yeah.
So if most of it stays over here, how much OH are we getting? Not a lot. Okay, so that's the point, is that we got lots of OH from the NaOH, but we get very little from the dissociation, ionization, whatever you want to call it, of the weak base. Yes? Like that? So all this yabbity 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 I've been doing is here. The weak base will produce OH minus, but it produces an insignificant amount next to the OH from the NaOH. So basically you just say, I'm going to find the OH from the NaOH and I'm going to ignore any OH that comes from the weak base. Yes? But let's prove it. Don't take my word for it. Let's do the calculations, which you will never have to do other than right this moment, because you'll just be like, it's insignificant. Here we go. Here is our Rice table for our weak base. Okay, we had 0.2 and the 0.4, that's already present. This is from the NaOH. Yes? Okay. Plus x minus x, we get a 0.2 minus x here, and we get a 0.4 minus x on the right. KB equals KW over KA. We get a value for KB. I got lazy and did my assume x is insignificant up here. So I didn't need to write it down in my equation. So far, so good. Okay, so now I'm just plugging in the, did I put my 0.2 and 0.4 in the wrong place? Yes, I did. This should be 0.400, and this should be 0.200. Okay, which means that when we solve for x, this should be 0.200, and this should be 0.400. So let's throw that in the calculator and see what we get. 0.2, or actually 5.5 times 10 to the negative 10 times 0.5 equals 2.78 times 10 to the negative 10. So even though I did the calculation wrong the first time, it's very similar. This is so much smaller than the 0.2 molar that came from the excess NaOH. Yes? Okay. Yes. Yes. Yes.
Like it said like number one and OH, right? Like what do we have left over?
Uh-huh.
Like because we have 0.20, sorry, 0.2
Molar. Yep.
for the B phase.
Uh-huh.
4.
Yep.
And then in the rice table,
Uh-huh.
ended up with 0.2.
Did I get them backwards in the rice table? Oh, okay. So I've been correcting a correction that was uncorrected. Dear God. Okay. No, it's because I did this question like 7 times and I kept having to put things I kept putting things in the wrong place. So let's look. This should actually be, this should be 0.4. Yes. And this should be 0.2. I can reprint this page for you if you would like. Okay, so you can replace it and not have a copy that's scribbled all over. Okay, and then we will have 0.4, and then we will have 0.2, which means actually this stuff down here was originally correct. So we'll go back to that original thing because I was correcting something where I'd made the mistake somewhere else. Is good now? Okay, I am going to make a new copy of this page for you so you can replace it. All right, so that's page 71. Now, the key thing is that after the equivalence point, the hydroxide or the POH or the pH or the hydrogen, whatever it is you are finding, will be dependent only on the amount of strong base in excess. Is good? All right. Hey, what happened? Okay. Ah. Summary. Can I get you to read the summary on your own time? Okay. There's before the equivalence point, the half that could either be before or after the half equivalence point. There's the half equivalence point, then there's the equivalence point, and then there is the after the equivalence point. So it's all explained there, it's all summarized there, and then there is a summary of the summary that compacts it even further. It says how far along is the reaction. If we have no base added, we have only the acid, so we'll use rice and Ka. We didn't actually do that today, where we said we haven't added any base, because that's fairly trivial, okay? At the equivalence point, you have both HA and A minus. Oh, sorry, before the equivalence point. At the half equivalence point, you have both and they are equal. At the equivalence point, you have A minus only. X. And after the equivalence point, you have excess OH only. So you guys today are going to do for homework, and I swear to God, I'm not being unreasonable today. You're going to do page 74, numbers 1 through 3, which is small. If you have time to do more than 3, go for it, okay? Actually, you know what? Let's also do number 4, just because it's one big question, a bunch of small questions. Okay? 1 through 4, in other words, 1 through 4.